Thanks. So thanks, Yasmin, for the organization and the support in the organization of this last webinar of BIPVBOOST project. In this third webinar, we are covering innovations at manufacturing BIPV system level and also providing an overview of the BIPV cost competitiveness in Europe. I will be giving a short opening and introduction on the project. We will then pass the floor to Elena Rico from Onyx Solar. She will explain the BIPV project catalog referred to Onyx Solar. Then we will have Xavier Otaño from Mondragon Assembly covering the new manufacturing line developed in the frame of the project, and we will have Pitts, Stefano Magadino, Schweitzer, Andreas Haller, and Tulips Post-Tassen covering their own product developments. And finally, we will have Elina Bosch from Beckley Institute covering the cost reduction along the BIPV value chain and on this overall BIPV competitiveness in Europe. So I will share my screen. Okay, please let me know if you can see the screen. Yes.
Yes.
Okay, so my name is José Maribel Esuani. I'm a project researcher in Tecnalia. I'm the coordinator of BIPVBOOST project. And as I said, this is the last webinar we are covering in the project, dealing with the innovation at manufacturing BIPV system level and overall BIPV cost competitiveness in Europe. Well, BIPVBOOST stands for bringing down costs of multifunctional building integrated photovoltaic solutions and processes along the value chain, enabling widespread near zero energy building implementation. So this was a proposal submitted in the topic demonstrates significant cost reduction for BIPV solutions in 2018. And luckily we were successful in this competition and had the opportunity to implement all the activities that we proposed in that time. Well, it is a consortium project led by Tecnalia in this case and composed by 19 partners from 7 countries, covering different parts of the BIPV value chain. In a nutshell, so the project is aiming to simply move on from iconic BIPV to the mass implementation of the technology. So we are aiming to progress towards the full adoption of the BIPV technology in the construction sector. The main objective was formulated based on the set plan for PV. So the ambition was to reduce the extra costs associated to the photovoltaic part by 50% in the project. And we intended to do so by implementing a series of strategies in different fields of activity, starting with advanced manufacturing, also covering the optimization of the development of certain BIPV products, implementing a digitalization strategy along the value chain, and also tackling standardization activities in the BIPV sector. I will cover now a few of the most of the highlights, let's say, of the results we achieved in the project. This will be further detailed by Xavier Otaño from Mondragon Assembly, but very briefly, we have developed a flexible taper stringer based on crystalline silicon technology. We have achieved a high degree of flexibility in the positioning of the strings, also in the manufacturing of flexible strings, both in length, also covering different cell distances, including variable cell distances within a same string, and also implementing inline quality control strategies prior to lamination processes, therefore, improving the productivity and quality of the overall production. As I say, this will be further detailed by Mondragon today. Then also in the frame of this webinar, we have a set of products that were developed and optimized in the frame of the project by Onyx Solar, Pitts, Schweitzer, and Tulips. I won't enter into the details, since this will be part of the today's speeches from our colleagues. Then on the digitalization framework, we had a previous webinar covering this topic already. This is also available online in WIP's YouTube channel, and you can go and check. But we have essentially tackled well, the development of, or the progress in the Enerbeam's Beam Solar tool, which is a collaborative platform for data-driven cost reduction on the BIPV process. We have also tackled cloud-based energy management system for tertiary buildings, including BIPV generation, storage, and manageable loads from 3E. And Technalia has led the activity in the development of the BIPV digital twin and the failure detection and diagnosis tool for BIPV. And also on the standardization framework, this was also part of the webinar series that we have created in the frame of the project. There was an intense discussion on how should BIPV be qualified, tested in the sector, and we have came up with 4 different testing procedures that could provide a better approach to the situation that we have today in the qualification of BIPV solutions. Today we have a fragmented standardization framework, and we have proposed a new combined approach that should better allow the testing of these multifunctional solutions. So we have worked on energy efficiency, energy performance in non-conventional scenarios, mechanical performance of BIPV elements, and also fire reaction. Luckily, we are in direct contact with ongoing standardization activities, and some of the testing procedures that we have developed in the project are now being discussed in these forums, which is a good news. And we have some available material in the public repository of the website. And then a brief overview on the demo realization in the frame of the project. We have the first demo site in East Fork in Puerto Llano in Spain, which hosts bifacial balustrade manufactured by Ionic Solar, and also a vocal floor using back contact technology, also manufactured by Ionic Solar. We have then well, the use case of this new manufacturing line developed by Mondragon Assembly and demonstrated at Onyx, which enabled the manufacturing of these well, sort of customized components, including also the combination of the glass solution from Onyx and the the fast installation solution from Tulips, the click and go system that Tulips will explain today. This is another view of this demo site. Then we have demo site 3 in Optimal in Mons, Belgium, which includes the well, the collaboration between Frisum and Schweitzer in this CIGS on metal roofing shingle, which was demonstrated in a multifamily house in Mons. And at last, we have the realization from PIDS, also in collaboration with Ionic Solar, with a battery kit developed in the frame of the project, which was demonstrated in a residential building in Morvenio in Italy. Last message from my side, we have public material available in the website covering different topics: cost competitiveness, status of BIPV in Europe, cost reduction roadmap for the European BIPV sector, market and stakeholder analysis, contribution of BIPV to NSEB, standardization, BIM. So there are many reports that are free to check, and you can download and analyze them freely. I let you the link. And just a final communication with a new project that we have launched in January that Technalia is also coordinating. We are extending now the scope to other integrated PV solutions, but we will be covering also BIPV and we should also generate contents, public contents that could well serve many people in the BIPV sector. So we encourage you to follow the progress in the website. And that's all from my side. So we can start with the speakers.
Thank you, Jose Maria. Now I would like to give the floor to Elena from Onyx. She will present first.
Yes. Just let me to share my
Yeah.
screen. Can you see the screen?
Yeah, perfect. Thank you, Elena.
Thank you. Then my name is Elena Rico. I'm R&D manager at Onyx Solar, and I'm going to show you the products that we have developed and manufactured during the life of a BIPVBOOST project. So let's start. In this case, we have work.
Elena.
Yes.
Sorry, can you make it full screen?
It's not
Please?
Full screen?
No. Well, at least I cannot see it full screen.
Now?
No, it's not on presentation mode. Maybe you shared the wrong screen, but
just a second. And now?
No. And we can move on.
Yeah, if
Sorry.
not, I will try to share mine because I have your presentation. Just continue and I will present.
You can try to push F5.
I don't know what's the problem.
Elena, if you want, I can present. I mean, you tell me when I should move, and then I have your presentation here. Don't worry. So here is in presentation mode. You can see my screen, right?
Yes.
Perfect.
Okay, so yes, I will start again. Here I'm going to present you the different products that we have developed within the project. Now, previous slide, please. Yes, we have based our work on the development of 3 different approaches. The first product was based on semi-transparent glass amorphous silicon pattern glass, competing with digital printing. The second product was based on low-cost, large format and thickness glass using bifacial cells for balustrade applications. And the third product was based on back contact solar cells, glass modules for 2 different architectural applications. One for walk-up floors and the second one for curtain walls. So next slide, please. So let's start for the first product, the semi-transparent glass amorphous silicon pattern glass, competing with digital printing. To develop this first product, we follow the methodology that you can see on the screen. We use the laser used in the manufacturing of BIPV modules based on amorphous silicon. This laser is used to get the different transparency degrees of to the PV modules. With this also we perform 4 different pattern designs based on this technology, and we follow a step-by-step process. The first step was to develop small prototypes of these 4 pattern selected, and these 4 prototypes were tested by visual inspection. We measure also the electrical response, and the samples were subjected to dam heat testing. The prototypes that successfully passed the test were then validated, and they passed to the next step of the development. The second step was to manufacture full-size prototypes with dimensions of 1,245 millimeters per 635 millimeters, and these prototype were also tested by visual inspection and the measurements of the electrical response. And once they passed successfully the test, they were validated and passed to the next step of the methodology. This last step consisted of the development of XL size prototypes with dimensions of 2,000 millimeters per 635 millimeters, and we follow the same methodology. The prototypes were also tested, and the good ones were validated and as a final product. Next slide, please. So here you can see the results. As I said at the beginning, we perform 4 different designs, but at the end of the process, 3 of them passed all the step and all the tests, the dots pattern and full stripes and partial stripe patterns. These prototypes show very good aesthetics and also the good electrical performance, the ones that were expected. Next, please. Then one of the patterns, in this case, the amorphous silicon partial stripe pattern, was selected to be demonstrated. So in this case, we manufacture 10 XL size modules that were installed as a BIPV facade solution at URAC facilities, and this demonstrator is being monitoring nowadays. So next slide, please. So let's see now the second product that we have developed within the project. In this case, it was based on bifacial cell modules, and the idea is to develop a product for integration in balustrade applications. So the methodology that we follow was based first on the selection of the bifacial PV cells, and then the idea was to manufacture different glass BIPV modules by following a progressive increase in the dimensions and in the thickness of the different samples. The process follow was also based on a step-by-step process, and the methodology was very similar that the one that we follow for the first product. First, we develop small prototypes, in this case with 2 different thicknesses, and the samples were tested by visual inspection. We measured the electrical response, and the samples were subjected to dam heat test. Once the prototypes passed all the test, the prototypes were validated, and also the process was optimized, and we passed to the second step. The second step was the manufacturing of full-size prototypes, in this case with a glass configuration of 8+8 millimeters. These prototypes were also tested, and once the results were successful, the prototypes were validated and passed to the last step of the development. This last step was based on developing XL size prototype of 2×1 meters and with a thickness of 10+10 millimeters. These last prototypes were also tested, and once the results of the test were good, the prototypes were validated. So next slide, please. So here on the screen you can see the different prototypes with the different size that we manufacture during the process of obtaining the final XL prototype. Next one. So in this case, with this product, we chose the full-size prototypes to be demonstrated. In this case, the prototypes were manufactured and integrated as a balustrade application at each office building located in Puerto Llano in Spain. So next slide. Here you can see another picture of the balustrade and the implementation. The surface that was installed was around 126 square meters with an installed power of the final solution of around 13 kilowatts. Next. So now here I'm going to show you the work performed for the third product. This third product was based on the use of back contact solar cells, and we developed BIPV glass modules for two different architectural applications, one for walkable floors and the second product for curtain walls. The methodology used was based first on the selection of the back contact solar cells, and then we built two different workflows depending on the final architectural application. In the case of the walkable floors application, the first step of the methodology that we used was to develop prototypes with dimension of 600 by 600 millimeters and with a glass configuration of 8 plus 8 millimeters. These prototypes were tested by visual inspection. We performed the measurements of the electrical response. The samples were subjected also to damp heat test and also electroluminescence. Once the tests were successfully passed, the prototypes for walkable floors were validated. In the case of the application of curtain walls, the first step of the development of this product was based on we made several designs of BIPV units using monocrystalline back contact solar cells. Among these designs, the different designs, one of them was selected to be manufactured and tested. So finally, once the prototype was manufactured, it was subjected to different tests and then validated. Next slide, please. So in the case of the prototypes of the products developed for curtain walls, as I said before, we made different designs, and the design that is shown in the right side was selected. In this case, we selected this design because we thought that it was the best example to study or compare the behavior of two different PV cells layout in the same module. Next. And here on the screen, you can see the final unit manufactured. In this case, we use dark blue glazing, and the results, the aesthetic was very good, and also the electrical performance was good and as expected. Next. And finally, the prototypes developed for the walkable floors application. On the left side, you can see the final prototype, the final module. In this case, this prototype has a front glass with an anti-slip treatment. And this product was also chosen for being implemented as a demonstrator. In this case, the walkable floor was installed also at the ISPOC office building in Puerto Llano in Spain. Next. The surface of installation was around 69 square meters and with an install power of 9 kilowatts. And that's all from my side.
Thank you, Elena. I will stop sharing. Thank you for your presentation. And now I would like to give the floor to our next guest.
Okay, hello everybody.
Hello, Javier.
I will share my screen. Let's see if it works. Hold on a second. Okay.
Yes, we can see it.
Can you see it in presentation mode?
Yes, we can. Thank you.
Perfect.
So for now you have 10 minutes and yeah, welcome.
Okay, let's try to do it in 8 if there's any question there. Okay, so Mondragon Assembly, we are a company that are building equipment, worldwide presence, and over 20 years doing solar manufacturing equipment. I'd like to focus on this presentation that, okay, there is a lot of PV industry in the mainstream modules. There are a lot of applications beyond mainstream modules and specifically today on BIPV modules. So when we talk about BIPV, there are different options that something can become BIPV. Some of our customers, they focus the BIPVT, if we can call it like this, of their modules on the aesthetics, as Onyx was explaining better than myself. Some others focus on how the module is light, and because it's light, it can do some specific things, being flexible, ultra flexible, or being part of a constructive element. That's also a little bit what Onyx is doing with making the glass photovoltaic, or some others are doing windows that are photovoltaic, as you can see in this picture. So okay, that's for the modules. What do we do in Mondragon Assembly to be able that our customers are able to manufacture this kind of different modules, specific modules? When our customers are looking for aesthetics, we have developed our tablet stringer BIPV option inside BIPVBoost project that allows us to have a different gap distance between cells, different string configurations. So having a very flexible tablet stringer that allows us to have a very aesthetic look of the manufactured module. We have also developed a tablet stringer flexible. This is BIPV, this is the MTS Flex, that is able to process back contact cells, Maxeon or Zebra, front and rear wired cells, welded, ECA, so very flexible for any kind of technology when it's when the search of the look of a panel that has no wires. And also we have developed for the very big and very small panels, when the customers are looking for a very wide variety of sizes, we have developed a layup system, the system that puts the strings on the glass, for glasses that are from 0.3 by 0.3 modules, small, extra small, to very large modules, 4 meters by 2 meters. That would be when we look for the aesthetics. But when doing a BIPV, our other customers are looking for the light and flexible modules. And in those customers, what they do to make this module light and flexible is they remove glass from their bill of materials. And when glass is removed, then some challenges appear in the process. So the first challenge is that the module may not be rigid. So how to transport the module from one station to another? Instead of having the typical belt conveyors, we have developed lines that do the transport of these flexible modules with robots. Or we put the future module on carriers, as you can see in this picture. Or we are transporting the module instead of the front glass, we are transporting on the back side of the module So instead of going sunny side down, we are producing sunny side up. That has quite a lot of challenges. One of the challenges on the lamination, we have to do laminators that are upside down, and without glass, there are challenges. New encapsulation materials are used, so new recipes, new characteristic, new features have to be added to the laminator. And then other tricky thing when doing glassless modules is the edge trimming operation. For the edge trimming, normally in classic modules with glass, the knife goes against the glass, and the glass itself is used as the reference point to cut all to do all the trimming. When there is no glass, we need to use this kind of CNC style cutting trimming machines, and this allows us to do shapes that are not only the square ones, but with rounded corners or other more fancy elements, fancy corners. And apart from not having glass, we see that on BIPV, the applications are more and more integrated on the building, which means that the glass of a window or the wall or the facade itself will be a PV application. When it's a PV application and it's part of the building, the challenge is on where to have the cables, the joint box, these kind of elements, or how to bolt or install them to the walls or to the building, start to be also a challenge, because it's not standardized and every product is customized. So we have developed specific machines for different applications for different customers. So for example, when people are doing things without junction box, where to install the diodes. So we have done an auto busing machine that includes the diode loading, or a specific station, totally standalone station, just for the diode soldering. Or when loading in classic, let's say mainstream modules, J-box is put with silicon. It's laid with silicon to the backsheet or the glass. But when we are not using glass, and instead of backsheet we are using other materials, the J-box with silicon needs special treatment on the material to be able to bond together. So we have developed machines, plasma machine, flame treatment machines, etc., to be able to do this linking. And then, as mentioned, the installation of the new modules, these new configurations on the buildings may require some fancy or special bolting systems that are not the classic aluminum profiles. So there are specific equipment, specific process steps that need to be developed for these kind of applications, adding some studs, some plastic nuts, some other elements to do the joining. And we have also developed this kind of machines. And this is what we are doing in Mondragon Assembly in BIPV related applications.
Thank you, Javier, for your interesting presentation. Now, as I said before, the question will be at the last point. So now I would like to give the floor to Stefano from PITS. Thank you.
Hi. Stefano for PITS, and we present the cladding system with the PV integrated. First of all, we show you the standard PITS cladding system. That is a joint facade system composed by panels made of fiber-reinforced mortar, coupled with insulation that can be rock wool or EPS. As we can see in the slide, this product can have a different finishing, different color, different smoothness, and as I said, is a dry system. Then there are panels fixed on the masonry walls by aluminum frame. We can see here a few different buildings made with the PITS panel. all other building, all different kind of building, hotel or housing or other kind of things. From this building, PITS cladding, we implemented this system with PV. Then the system is a combination of conventional PITS product with the photovoltaic to have a BIPV system. In this way, we have a thermal insulation, good level of sound insulation, with also production of energy. Thanks to BIPVBoost, we developed two types of product. The first one was the PITS panel glued with the PV shells, just 3 + 3 millimeter of glass provided by Onyx, and another option with lightweight PV CHICS technology. We did a few preliminary tests, and at the end, we continued with a single product. And this one was the 3 + 3 millimeter of glass, which one we also did the demo site. As I said, the products were tested. Also, we achieved the product at TRL 7. And we did suction test, shocking test, fire reaction test. And also now we are going on and we try to achieve TRL 8 validation to achieve the CE certificate and sell the product. With this product, with the EPITS, with 80 millimeter of rock wool, we had a system of around 41 kilogram per square meters, thermal value of 2.11 square meter Kelvin on watt. But the really good characteristic is the class reaction to fire, because we achieved the class B S1D0. That is a really high value for a facade with the PV integrated. A few slides of the demo site in Morbegno in Italy, where we installed 9 kilowatt on the facade of two twins housing buildings. And these two buildings were realized already with the PITS cladding. Then we removed the last rows on the top of the building, and we replaced with the new ones with the PITS system. With the PV. Few details during construction phase. Some zoom of these chairs provided by Onyx. Like I said, these chairs can have a different effect. In this case, there is this green golden effect. And on the bottom also the inverter. The PITS was installed in 4 sides of the building, then 4 orientation, north, south, east, and west. And for this building, for each building, we installed 1 inverter for each side. Here, short video where it's possible to see the installation. As I said, is a dry system, then really easy and quick to install the panels. Sorry. And this is the final result, where we see the EPITS on the top of the building, and what we think and what we believe that is that in this way we gave a value of the building, not only from a technical point of view or profit, but also an aesthetic from aesthetic point of view. And this was integrating the PV cells in our cladding system. That's all.
Thank you. I would like to give the floor now to Andreas Heller from Schweizer.
Thank you very much, Elena. Jasmine, I hope you can see my screen.
Yes,
Okay.
we can.
Thank you. So, my name is Andreas Haller, as it's called already, from the company Schweizer AG in Switzerland. And we have since quite some time a roof integration system, this system Solrif, and we have used this system first as a vehicle for the design and for the production of the demo site CIGS modules, and also to improve the system itself. So I give a few words to the system itself in the beginning, and then some words to the achievement in the BIPVBOOST project. The Solrif BIPV roof system consists of a few simple components. You have the roof substructure, then you have the modules, which had in the beginning had to be the same size, the same type, of course. Then you fix them with the clamps on the roof substructure. You have standard flashings for tile roofs around. And before the BIPVBOOST project, part roofs were limited to rectangular shapes for customized with customized flashings. You had no limits. You could cover a complete and complex roof. So features and advantages. This Solrif roof tiles, they replace the conventional cladding of the roof, and this saves for new construction and for roof renovations, of course, a lot of material and a lot of CO2. It's easy installed with standard flashing systems, especially for part roofs. It has better stability than rooftop installations, can resist much higher snow loads. It's suitable for almost the typical or all the typical sizes of the standard modules. Of course, the risk of tile breaking is not here anymore. It has better aesthetics. And what is important, we do not sell these modules as Schweizer. These modules are offered by PV module manufacturers as BIPV version of their standard modules. For installation and operation, there are quite some features available. There are colored modules on the market. You can add snow guards. You have holders for lightning protection, and for service, you can detach every module individual in the field. Now, the achievements within the BIPVBOOST project. We have extended the flashing also for complex field shapes. You can see you have these inner corners and on the top side, on the bottom side, and of course left and right can now be managed with standard flashings. This allows for these part roof implementations or also for full roof implementations. We have also on the planning tools, we have implemented the module family function. Up to 3 modules with the same height and different widths can be specified as a module family and used in the same roof for the design. This enables a significantly better utilization of the roof area with active modules. Then to enable even inexperienced installers to successfully install full roof efficiently, we have created a library of standard flashing details. These solution examples are freely available as CAD data from the Solrif website. You just can go to this sketch of this house and then click to the detail you actually want to see, and then you can download these details. And one of these most complex details are with existing older roof windows. They are really complex, and also for these solutions we have appropriate example situations. For the installers, a significant reduction in installation time was achieved with the development of an installation gauge, as the clamps can now be positioned and fastened by only one installer instead of two. This is really important. It was a feedback from the installers that this is time consuming and should be speeded up. So we were able to do this in an action within the BIPVBOOST project. And last but not least, in the demo site 3, all these complex design details, they were implemented for this full BIPV roof. Part of the material for this roof could be prefabricated and delivered with the CIGS in-roof modules that have been also developed and produced for this project, and other parts were supplied by third-party manufacturers and partly adapted on-site. We have a roof, an east roof, a west roof. We have a full integration, 2 different modules, and almost all complex situations you can imagine you can find in this project. For further information, please refer to the Solrif website. We have also a web installation for the planning tool, this ProSolrif, and of course in BIPVBOOST there will be the product catalog available quite soon. Thank you very much.
Thank you, Andreas, for your interesting presentation. Now I would like to give the floor to Paul Stassen from Tulips. He's the last partner who will present in the BIPV product catalog. So, Paul?
Hello. Good afternoon to you.
Good afternoon. You have 10 minutes. Thank you.
Thank you. Thank you. I would like to present our developments in the BIPVBOOST project. Second. So the goal is to achieve the cost-effective BIPV ventilated facade systems and to achieve 50% cost reduction. So what we did is we developed the click-and-go new substructure, what we call the flex frame, which is simplification of the design and the reduction of components. We reduced the labor needs for assembly and the mounting process. The reduction of the weight and the transport volume, and we made sure that it's all very easy to mount, and also the improved versatility, so adaptable for different photovoltaic panels, both vertical mounting, tilted installation, and flexibility in terms of the dimensions of the photovoltaic modules. When in the beginning when we started the project, we had only one module which needed quite some time, and we speeded it up to 2 minutes per module. So basically the current production is 30 modules per hour, and we could further improve it in the near future to 60 modules per hour. So it could be easily combined with Mondragon production line. What we also did is, in addition to the optimization, so we optimized the easy installation and the versatility, but we also built some samples, some small demos to test the functionality. And you also see here both the vertical installation on the right side, but also the tilted installation on the left side, combined with traditional facade materials, in this case, aluminum composite cassettes. So the feature of the system today is that the click-and-go mounting for ventilated facades can accommodate almost any solar module size, up to 2.80 meters long and more than 1 meter wide. It's very easy to design and easy to engineer, and we come back to that later. It's ultra fast and safe installation. So think about depending on the situation, 0.6 to 0.8 hours per square meters, and that has been already demonstrated in practice. And very important for insurance companies today is that each solar panel is individually exchangeable. So the click and go is really click and go. So you install it without screws, so it's sliding and clicking, and it's very secure by a rotating element, and you can also by taking the rotating element, you can easily take the module out again if needed, for instance, for inspection. The whole system is designed for long life and durability, and it is fully tested and certified, and it's maintenance free. So the USPs are easy, fast, safe, and beautiful. Versatility, it's very versatile and flexible for ventilated facades. And because we operate automated gluing and assembly process, it's controlled, secure, and it's fully prefab produced. With the with the standard produced solar modules, glass, we offer 200 to 205 watt peak per square meter, which means 140 to 150 kilowatt hours per square meter, depending on the situation. In the project, we also demonstrated the system at the Mondragon site in cooperation with Onyx, and it is a beautiful result. The cost of the system, when we talk about mass-produced ready-to-install systems, so click and go, plus the frameless module, black, 60 cells, including inverters and cables, is between 375 and 400 euros per square meter. Then we talk about mass-produced glass modules. And when you were planning to build a ventilated cladding facade anyway, and then you think about the extra costs for the photovoltaic functionality, then it's only 175 to 200 euros per square meter. During the BIPVBOOST project, we proved that we could reduce the cost of the click and go mounting system by 50%, so we achieved the goal. We do this for the real estate owners who have a lot of demands to fulfill due to new European legislations, but also for other reasons, like the upcoming taxation for CO2 emissions. And the issue is how to achieve these new requirements, especially in the building industry of high fragmentation and high diversity. How do you deal with that? So one of the questions we are facing as an industry is how are we going to make the implementation process very efficient? Because what we see is that in the whole process of implementation, you have, as a system supplier, you have to talk with a lot of stakeholders in the industry. So you want to talk to the real estate owners, but in the meantime, you have to talk to if you're dealing with facade builders, architect, construction partners, and to you're also competing with competing component suppliers. So we came up with the BIPV World platform for automated and better BIPV designs and lower cost, because we want to slash the cost of the implementation cost for BIPV. So it's a platform for easy design and efficient implementation of aesthetic and cost-effective BIPV systems. I hope that the video will work.
Because of climate change, fossil energy challenges, and historically high energy prices, renewable energy solutions are crucial. Laws and regulations are in place, but most people lack the knowledge and experience to tackle the energy transition. Building integrated photovoltaics or solar facades can address these challenges, especially when structured and automated through a fully digitalized supply chain. Introducing BIPV World, a SaaS platform enabling professionals to easily add solar power to any building design, directly showing its aesthetic value. And with both costs and revenues fully transparent before construction starts, financial risks are minimized. Digitalization also concentrates and shares the scattered knowledge and industry-wide expertise, accelerating processes and the tailor-made energy transition for buildings, while grid capacity problems are solved using several techniques. Because of the centralized platform, suppliers of BIPV products and services can greatly benefit too. BIPV World minimizes implementation costs and complexities and also eliminates industry-wide scalability issues. BIPV World enables the easy design and implementation of aesthetic, cost-effective BIPV systems by connecting providers and customers with ready-to-install prefab systems, turning potential complications and additional costs into attractive, safe opportunities and a wise financial choice. In other words, BIPV World is a crucial platform for realizing ambitions, complying with legislation, having aesthetic power generation, and earning money with the facade.
I'm going to skip this sheet, but the platform is basically a location where you can find all the systems that and all the solar modules that are available, and then you can download Autodesk Revit plugin. The architect can easily make a design, and then immediately the data that the architect, the data from the drawing is communicated to the platform. So not the drawing, but the elements that the architect has designed. And then the architect or the developer immediately get a cost indication for the complete system. And it's all made possible by a digital backbone, in the BIPV World platform. We invite also other suppliers of system to join the platform and to make their systems available in this tool, because this is, in our vision, the only possibility to scale BIPV solutions across Europe in a very efficient, cost-efficient way. So what's happening is that the BIPV World is helping the architects to make the right choices, helping facade builders also to make the right choices, to have the right design that can be, from which we know that it can be made, and that you have a very quick and good process to offer a good proposition to the real estate owners.
Thank you, Paul.
Yeah. So
thank you, Paul. Sorry.
No, I understand. So if people want more information, please contact us.
Yeah, I would like to remind that this webinar will be uploaded. So in case you have any other question, you can always reach us. And that was for BIPV products catalog. Now I would like to give the floor to Elina Bosch from Becquerel Institute. She will talk about the cost reduction along the BIPV value chain. So thank you, Elina.
Yeah, thank you, Yasmin. So in this presentation, I'd like to give an overview of potential for cost reductions for BIPV products and the status and also perspective for BIPV competitiveness in Europe as well. So very quickly, Becker Institute, we are a research and consultancy company. We are established since almost 10 years in Brussels and since 1 year in France. And we focus on, well, solar PV and also related technologies. It can be storage, e-mobility, and buildings. So first, I would like to present how we typically can assess the competitiveness of a BIPV system. So BIPV being both a construction element and also an electricity generation unit, there are different relevant ways to approach the competitiveness assessment. First, we can assess the competitiveness at a construction component, in which case the component cost of BIPV will be compared to other typical construction materials. It can be ceramic in the case of tiles, it can be glass, it can be concrete. Then we can a bit enlarge the scope and compare a BIPV full solution to alternative construction, conventional construction solutions. So in which case the comparison will be made between BIPV system and, for example, a glass facade or a full roof based on ceramic tiles. Since BIPV also allows to generate electricity, it can be also relevant to calculate the cost of electricity generation, in which case one can compare the results with electricity produced with BIPV, for example, or also base the comparison on retail electricity prices or wholesale electricity prices. And finally, one can have a more holistic approach and consider not only the cost, but also the revenues. So all positive and negative cash flows that will occur on a BIPV system typical lifetime. Usually we consider 30 years. And this gives net present value in euros, which is then normalized in euros per square meters, as it's a more relevant unit in the construction industry. And so it's this fourth competitive approach for competitiveness assessment that I will be presenting in the following slides. So as I was mentioning, the idea is to put in balance all costs and revenues associated with the investment in a BIPV system. And we are not only considering the total investment cost in the BIPV system, we are considering the extra costs of BIPV. This means we're looking at the additional costs that are needed to have a BIPV solution compared to having a conventional construction solution. And then in terms of revenues, we can have typically savings on the electricity bill. And then for injected electricity, there could be some feed tariffs applicable or subsidies and incentives in certain countries. Some countries even have BIPV specific subsidies or incentives. And in the end, the question that we try to answer is whether it's profitable to make the investment in a BIPV solution compared to a conventional construction solution. So to establish a bit the benchmark of BIPV competitiveness in Europe, we took 4 different reference cases, 2 residential cases, single-family house with BIPV on the roof, and a multi-family house with BIPV on the facade, and then 2 non-residential reference cases, 1 semi-transparent curtain wall, and then a roofing solution for the industrial building. For the residential BIPV system, overall, the results show that the solution can be profitable for the residential roofs. the competitiveness level can even be very attractive in some countries. This can be thanks to the good irradiation conditions or to the presence of some attractive support schemes. For the multifamily house, because we are on a facade integration, we have a little less favorable irradiation conditions, but still competitiveness is reached in most countries or very close to be reached. For the office building reference case, so we have a curtain wall with semi-transparent solution, so quite low system power density, and we also have a vertical tilt, which is considered. As we are not in the residential sector anymore, electricity prices are slightly lower, so that also impacts the reduces the potential of savings on the electricity bill. So when irradiation conditions are quite good, in fact, the solution can be almost profitable under the considered system characteristics. And if we have a industrial building with a BIPV solution applied, well, integrated to the flat roof, here again, in countries with good irradiation conditions, the solution can be profitable, even though in the industrial segment, again, electricity prices are lower, so this reduces the savings potential. There are several areas of improvement and innovation for BIPV products. In the BIPV Boost project, as it was presented well in the previous presentations, cost reduction have been addressed all along the value chains, from the studies part up to the use phase. And the cost reduction potential for BIPV product is not limited, of course, to improvements that are developed in projects such as BIPV Boost. BIPV system can also benefit from improvements and cost reduction which arise from either the construction sector or the PV sector. So overall, it's both a question of market pull and technology push, which can allow to further reduce the cost of BIPV solutions. Very quickly, the idea is that by combining all of the different cost reduction potentials from BIPV Boost, but also external cost reduction areas from construction and PV sector, there is a potential on one hand to further enhance the profitability of BIPV solution, which are already competitive. So that's what is presented on this slide. And if we look at solutions that are maybe in some under some configuration not yet profitable, with these cost reduction potential, there is a possibility that profitability or competitiveness threshold is reached in different conditions or boundary conditions. In general, it's not competitiveness of BIPV is not a question, not only a question of cost. There are other elements which highly impact the competitiveness that can be achieved. It can be location-specific factors such as the irradiation conditions or even the applicable support schemes. It can be project-specific enablers, so the electricity price that is paid by the customer that will be installing a BIPV solution. Also, the ability to self-consume, the tilt and orientation of the areas to which a BIPV solution can be integrated, and then also BIPV-specific factors such as, well, we mentioned this cost, but also system power density. I just mentioned this, one of the important influencing factor is still the support schemes. Here are 3 examples of countries or regions where BIPV specific support schemes have been introduced. In Switzerland and in France, they take the form of a investment support, and in Belgium, it's a specific grant rate for green certificates, so only applicable in the region of Brussels. And in some cases, the existence of this BIPV specific subsidy can really either give a further push to BIPV competitiveness, or in some cases also be a game changer and really allow the BIPV solution to go beyond the competitiveness threshold. So overall, we have a very wide variety of possibilities with BIPV solutions, most of which are already competitive in many configurations in many countries. There are important cost reductions potentials, some of which have been already tackled in BIPVBoost project, but external factors can also play an important role. And so overall perspectives for BIPV from a economic point of view are promising on the short and medium term in Europe. On the BIPVBoost website, you will find different reports which go more into details, either in the competitiveness assessments or in the cost reduction roadmaps for BIPV solutions. So I invite you to have a look at this report, and I'm available if you have any questions.
Thank you, Elena, for your interesting presentation. Now I would like to give the floor to Jose Maria. I don't know if he's still here. This is our last webinar, and yeah, if not, I would like to say thank you everybody to join us in this several series of webinar. Everything will be uploaded to the BIPVBoost website, so stay tuned for this one. It will be, I think, next week. We cannot hear you, Jose Maria.
Oh, sorry. No, nothing to add from my side. So thanks everyone, all the speakers and all the attendees for being here today, and thank you, Jasmine, for the organization. And yes, as you said, all the material will be publicly available in the YouTube channel from WIP.
Yes.
And all the public reports and the contents that we generated during the project are still accessible and will be accessible for at least 1 year. So yes. We encourage everyone to go and check.
I don't see any question in the chat, but if you have any question, please write to us, and I will be happy to put you in contact with a specific person in charge. Thank you, everybody, again, and stay tuned for more information about this BIPVBoost project that is coming to an end, but the website has all the information in case you are interested. Thank you.